Hello, good morning. We are here today to talk about how to find 50,000 needles in 5 million haystacks. This talk is going to be about a combination of network traffic analysis, threat hunting, and machine learning. So that's what you should expect to see here. Before, we would like to introduce ourselves very briefly. I'm Veronica. I'm from Argentina. I'm a malware traffic researcher and threat intel analyst and cognitive threat analytics, which is part of Cisco. I'm also a co-founder of the Maze Lab hackerspace back in Buenos Aires. I'm here today with two of my colleagues, Karel Bartosz, he's from Czech Republic, network security researcher, and Lukáš Machlica, he's from Slovakia, and he's also doing network security research in our group. So let's get started. Today we are living in very interesting times. Our world is connected as never been before, right? From fridges to cars to anything. And this is very useful sometimes. And this connectivity is because sometimes we want it to be this way, right? And sometimes because we forgot to change the default password, which happens more often than we think. And we are facing unique challenges, not only because of the new tricks, methods, and sophistication or lack of that malware authors are bringing to the table every week, every month, but also because of the scale of the attacks. Our organizations or users are one click away to getting infected almost every single day. From malicious advertising to adware and phishing being one of the biggest sources of infections nowadays, to more complex threats such as ransomware, I'm sure you heard a lot this year, banking trojans, information stealers, remote access trojans, and so on. So this means that the question that we ask ourselves has changed in the last couple of years. The question right now is not longer if an organization is going to be breached by one. It can happen this week, it can happen next year, right? The thing is how to be prepared against that. And if we assume that at some point organizations are going to be breached, we are going to have active infections, right? Then it's clear what we need to do is basically look for these threats that already bypass all the security measures that we have in place. Because we have antiviruses, we have IDSs, we have all these, right? But what happens if there is something new that already bypass these security measures and is on our network? So, but this is basically the definition of threat hunting, which threat hunting assumes compromise, okay? They assume that you are already compromised and they have a series of methodologies and techniques to actually search for these threats on your network. That's what many companies do. And this is what I do, big scale, for a living. So my job is not actually quite like this. And it's very interesting to see the comparisons, because in normal hunting, you actually know many things. You know the environment where you are going to hunt. You know your weapon. You know, and more importantly, you know your prey. You know what you are hunting for. You know how it looks like. You know the colors. You know the size. So you know if you have good chances or not. But in my job, in many of your job, this is not like it. Because I don't know what I'm hunting for. In my network, I don't know where to start, and I'm looking for things that I already bypassed the antiviruses. I already bypassed all the signatures. I'm hunting for something completely unknown. So this is how common network looks like, and when I have no idea what I'm looking for. And in my case, it's dozens or hundreds of different networks. So what do we do here? It's not actually true that I don't know anything. I'm not truly hunting for the unknown, because there are some things that we already know. Because we know how banking Trojans communicate, right? We know banking Trojans in general. We know that their goal is to steal credentials from the user. So they will, at some point, when they steal the credentials, they need to send them out, okay, to the attackers. If we have a remote access Trojan, that piece of malware actually needs an active communication because it needs to be actually controlled by the attacker. If we have exfiltration Trojans, it's actually the same. Click fraud is actually the same. So there is one thing that they have in common, and that is the need to communicate through the network. And there is where we can take this need to communicate, exploit it to make it our competitive advantage. And this is what we do. But the problem, the next problem is like the sizes of our networks. We are talking about every user in an organization has 3, 4, 5, 6 devices. So it's no longer that our network is hundreds of devices. It's that multiplied for 5, right? So we are talking about a lot of data. But wait, big data is no longer a problem, not a challenge anymore. We know how to work with big data. We have the software, we have the storage, right? This is not matter of discussion anymore. And the problem now, the next problem is I cannot replace humans, right? Because the threat expert knows where to look at, knows if they are looking at the network. If I'm looking at the network, I know which things are interesting. I can tell, okay, this piece of proxy log, it seems very suspicious to me. And how can we do that? And here is where machine learning comes to place. Because what if we can teach machine learning to actually see through my eyes? What if we can teach the algorithms to see specific features that I, as a threat analyst, I could look at? So this talk is it's going to be about this. Because machine learning, combining these 3 things, we can go from this picture to actually something more like this, where we cannot longer sit on a network and say, I don't know where to look at. We can have specific things pointed to us, saying, okay, instead of looking at everything, look at this specific group of interesting things. And not only that, but also look at these things that seem similar together. So if we have 1 infection, it may not mean anything, but if you have 3 infections, then you have more information to correlate, right? So this talk is going to be about combining these 3 things. We are not going to present a novel revolutionary machine learning algorithm, but we are here today because we want to share our experience on how we combine this. Because it feels like every day I wake up and read the news, it seems that it's so depressing. It's like all the same, right? And we seems like as defenders, we are always 1 step behind. So how do we position ourselves 1 step ahead of the game? And the answer is not secrecy, right? And we believe in transparency and collaboration. And we think that if we explain how we work, what successes we had, we can take this step forward. And we combine these 3 things in a real-life implementation. We face different challenges, and my colleague Karel is going to walk you through those challenges.
Thank you, Veronica. So we, as network security researchers, are facing 4 major challenges that we believe prevent machine learning from being successfully and massively used in practice. And a few years back, addressing those challenges would seem basically like a Star Wars. But in the following 40 minutes, we are going to show you our solutions to those challenges, and that it's not such a Star Wars anymore. So the first challenge is high dynamics of malware. Network environment is highly dynamic, and malware samples and malicious traffic is dynamic even more, because attackers are trying everything that they can and change everything that they can to bypass the current security systems and to remain invisible. The other challenge is the lack of labels. To build a successful and reliable and precise classification systems, we need a lot of labels. And in network security, this is a big problem. And what's even more troubling is that obtaining additional labels is also very costly and very painful process. Another challenge is large-scale training. To make the classifiers work on different companies and on different networks, we need the ability to train the classifiers from big data. And the last challenge is actually how to automate all these things, how to retrain the classifiers automatically from the data to react on the ever-changing network threat landscape. So this scheme summarizes the 4 challenges that we will be talking about today, and I will be talking about the first 2 and how we succeeded in here, and Lukáš will be talking about the other 2. So let's start with malware dynamics. So attackers change malicious code or payload on daily basis to bypass the signatures-based systems, right? And instead of doing the static analysis, we decided to explore another, let's say, feature or need what the malware traffic does, and that is the need to communicate over network. So for that, we are using metadata, more specifically proxy log records, that is an information acquired from the header of the packets, and it has information about who is communicating with whom and how much and when, but we don't see the content of the communication, which also makes us HTTPS agnostic. So when working with this data, this gives us an opportunity to be invariant against all of the malicious code or payload changes, right? But the attackers do a lot of other things, a lot of other changes that we need to consider. And that includes the change of server IP addresses or host names to bypass the blacklists or feeds, or they change thinking time or URL resources or parameters to bypass anomaly detection systems or other behavior analytics. So to tackle this problem, we need to build an invariant representation that would be robust and invariant against all of these changes. And I will be talking about it right now. So the first step is to extract some basic features. We are using 2 types of features. The first type are the features extracted from the individual connections, from the individual requests or flows. And they can be URL based. For example, you can extract Ngram statistics to detect DGAs, or you can extract some distribution of special characters to detect, let's say, tunneling data through URL. And we have also other fields at disposal. For example, the number of bytes transferred up and down, or HTTP status, referrer, MIME type, user agent, and so on. So you can extract hundreds of features out of these fields. Another type of features besides that are the features computed from the global visibility, because we have that, so we can actually compute features like, let's say, user domain popularity, or the popularity of the server IPs, or the popularity of hashes. And we can also use some external sources like GUIs to work with the age of the domain. But it's not that simple, because if we just would extract all the features and put it into the classifier, it will not work, because of this. Here you can see 32 different malware categories, that are the rows, and the columns are the features, the flow-based features. And the yellow color means that all the feature values for that particular malware category and for that feature, all the feature values are different, while the blue color means that the features are the same. So as you can see here, it might be even quite hard to actually train one classifier for one specific malware category, not mentioning one classifier that will be detecting all of the categories. So we have to come up with something else, and that is the bag-based approach. So what we do, we take the incoming connections and we group them into bags. And one bag is basically a set of connections from one user to one domain or one server IP. So it describes the communication between a user and a domain in time. And we can extract very interesting features out of that, which can be then put into the classifier, and such classifier would be able to detect a reasonable amount of variety of malware samples. Here you can see examples of far malicious bags and one legitimate bag. And I hope you can't see the individual characters, because then you would be focusing on the flow-based features, and that's what we are trying to avoid. But if you have a look at it from the distance, you would see that the URLs within each malware bag have similar structure. They are not the same, but almost the same. There is a change here and there, but as opposed to they have the similar structure, as opposed to the legitimate bag, because if you are visiting some legitimate site, then you are downloading a set of images and iframes and JavaScript, so the URLs look completely different. And this is exactly the thing that we are trying to capture here in the representation, the malware dynamics. So we got inspired from the action recognition, where you have a sequence of images and you want to detect some actions. So for us, flows are the images. One flow is one image, and the back, the whole communication, is the video. So we are trying to actually recognize malware videos from the background. So here you can see the overview, and I'm not going to go into the details, but we start with the initial connections. We group them into the bags, extract the basic features I was talking about, and then we take, for every feature, we take all the feature values for all the flows within a bag and compute different self-simulatory matrices, and then we convert them into the histograms to increase the invariance, and finally we combine everything into one feature vector and apply our optimization algorithm that would actually learn all the parameters, for example the number of bins or the bin widths and everything, that will learn all of these automatically from the data. So the representation would be specifically tuned, data tuned to the malware samples. And if you are more interested into that, please have a look into our Unix security paper from this year. So that was the first challenge, how to capture the malware dynamics and how to make a representation that would be ideal for this problem. Another problem is the mistakes in labels, because what we typically have is a small amount of reliable labels. Basically, most reliable are the labels that are manually created, right? But this does not scale. So, for example, we all know that Mr. Yoda is a good guy, right? But what about the rest? Well, for the rest, we can use other sources, for example, blacklists or feeds, that are not that reliable, and label the remaining connections or the remaining network traffic. But the question is whether there will be some other mistakes, and there will be, right? So if we can actually use it for training a robust and reliable classifier. And we believe that if you would use the traditional approach, it's not possible, because the classification model would be too polluted with the mistakes. So instead, we suggest to use a different technique, which is called multiple instance learning approach, which can actually handle these types of mistakes. And I'm going to show you just the idea. So at the beginning, we have a set of connections that are those black lines, and they are either legitimate or malicious. So if the connection is legitimate, then there is the green minus sign. If the connection is malicious, then it is denoted with the red plus sign. But we don't know the true label, so we apply blacklists or feeds or whatever is available and label the connections. And as I said, there will be some mistakes, right? So if there is the M, that means that, for example, legitimate flow is classified as malicious or vice versa. And if you put it like this into the classifier, you can expect that the classifier will be behaving poorly because of the polluted model, because you will be forcing him to adjust some kind of hyperplanes in the space where it shouldn't be. But instead, if you use the bag approach and combine the individual flows into bags and label the bags, then you have the ability to dramatically reduce this negative effect. And it has two advantages. First, you don't need to label everything. You don't need to label each individual flow. You just need to label the bags. And the bags could be everything, let's say all the traffic from a user. If you know that the user is infected, that is enough, and you don't have to say specifically which flow is the one that caused that, because the classifier would just take only a few representative and most interesting flows and put it into the model. And for that, we have a modified SVM classifier modified for this type of mill approach. So again, if you are more interested, please have a look at our ECML paper. So we were kind of successful with deployment of those back approaches, and we were able to actually classify a nice variety of malware samples, including CryptoWall, exploit kit, or different banking trojans, but Veronica will be talking about it after me. So that was just the explaining of how to build a reliable representation and how to use weak labels for classification. But there is another important step, and that is how to build reliable classification models on the top of that. And this is something that Lukáš will be talking about it right now.
Yeah, thank you, Karol. Well, hello. Okay, so this is the third challenge. And the question is now how to build a reliable data set for training, and even what models to use in order to be capture the malware. So the first thing that I will be talking about is how to sample your training data to get a reliable training set of your classifier. The first thing is that per day we process around 10 billion of requests, which is a huge number. And in fact, these requests cannot be fully labeled, of course. Just a small portion of them can be. Another thing is that the problem is very imbalanced. Only some of them are malicious, but most of them is legitimate or benign behavior. So in this picture, you can see the green, red circles that right now represent the known legitimate samples, and the bugs represent the malicious ones. So if you would train a classifier, you would end up with the boundaries depicted here. But of course, they are trained only on the known stuff that you have labeled. Whenever you introduce the rest of the traffic, you will figure out that the boundaries are in fact very, very weak, and that the precision of the classification goes down. So what you can do, obviously, right, we can use also the unlabeled samples, and in that way strengthen the boundaries of the classification. But the question is how to do that and how to avoid the processing 10 billions of samples. So what we do, we have a set of statistical simple classifiers that in fact process the data, and we get a maliciousness score. We rank the traffic according to the score, and instead of taking all the samples, we take only the top end samples and collect these across a longer period of time to get a diverse data set. In this way, in fact, we can get rid of the benign or not interesting samples and focus only on those samples that are populating our space of interest. Another thing is how to get rid of malicious samples in the unlabeled set, at least those that mostly harm the classification. And for this reason, I've used the positive unlabeled training principle. That is quite simple. You have a malicious labeled malicious sample set, and you take a small portion of samples as spies, and you inject them into your negative training set. And then you train a binary classifier from these two sets, and then what you do, you just score your unlabeled data, and you will find a threshold below which none of the spies or the known positives occurs. And in this way, you can kind of discard the most problematic samples and get a much more cleaner negative training set. Okay, so now we have some training principles and representations. The question is what classifiers we use and how we use them. So the first one is SVM, as Karel was already talking about, for the mill representation. But the other one that we use is random forest, a very popular technique used in many state-of-the-art machine learning techniques. It has one nice property that is randomness, and how do we use it? Is that instead of using the full feature set of full features that we have, we sample only randomly a smaller subset of these features and train a specific instance of the model at a time only from the subset. Whenever the model is retrained, it uses again another random subset of the features. So therefore the traitor cannot be sure exactly what kind of features we are using at the moment. And we use it prevalently for per vector classification. What I mean by that is, for example, that if we want to detect or use communication using DGA, then we can extract single feature vector from the domain name, and we can assign directly a label to this single feature vector. So it's just a single feature vector classification. However, in that case, of course, you need labels on the level of individual vectors, which is quite expensive and often not possible. Therefore, other principle we use are neural networks. Again, there are a lot of different architectures that can be used. But we use the specific architecture, and the classification right now is performed on the level of users, not on the level of vectors. And how we do that is depicted here. So we have a traffic of user J. Smith. He has several requests, for example, going to Google, Gmail, some raw IP, and CNN, and so on. We can extract feature vectors or representations that Karel was talking about for each of these requests. What we do is then that we propagate all these feature vectors related to full traffic to the first hidden layer in the neural network already trained. So that means that now we come up with a new representation, and we got this new representation again for each single request. And what we do next is we do pooling, very common in convolutional neural networks. And the pooling is in fact an aggregation where we aggregate all the feature vectors related to one host name or one domain name. So at the first hidden layer, we now get one feature vector for Google, one feature vector for Gmail, and so on. So these feature vectors kind of depict the communication of the user going to these domains. Then we propagate all these feature vectors next to the second hidden layer, and again we do the pooling, and we get up with a feature vector representing the full traffic of user J. Smith. And finally, to be able to get a classification score, we propagate the feature vector to the third hidden layer, and we get a classification score, and this is just compared to a threshold, and then if higher than, alarm is triggered. So this is how we classify user traffic and how we use the context. Okay, so we have a few classifiers. Now the question is, how does the classification topology look like? The first thing is that the classifiers have to see all the traffic or classify every traffic, so all the 10 billion requests. And this is quite time consuming. Therefore, we use first just a prefiltering layer, which is also a classifier, data-driven classifier, but it uses just simple features that can be extracted quite simply. And then at other levels, we can use more advanced techniques and more advanced feature vectors. So for example, you can see here the traffic that is filtered by the first layer, and it can contain also false positives or false detections, but it's just the first layer, and it should just filter out ordinary benign traffic. So at the next level, what we have here is a set of classifiers which can be quite generic. They are, for example, in this case, we can detect DGAs or communication using domain generation algorithms, or we can detect obfuscated URLs. These detectors or classifiers are already highly precise, so they can distinguish easily between malicious and legitimate communication, but they don't give you any higher overview of what is going on there. And therefore, we have the last level, where we have specific classifiers focusing directly on specific malware communication, such as phishing, click fraud, or CNC communication. And when you follow the classification path, you can also say, okay, this was a CNC communication with a domain generation algorithm and also using obfuscated URLs. So this kind of information that you get from the full classification architecture. So this was the third challenge, and now we have also the models, we have the architecture, and the question is where to get the labels, how to update the labels, and even how to update the whole system when something changes. So the first very important module is the active learning module. It consists of a human analyst. The input to the module are detections. These detections are coming from the general classifiers and all the classifiers, in fact, that we have. And the role of the human analysts is analyze and confirm the maliciousness of the provided samples, but also to categorize these samples into specific categories, such as click fraud, data exfiltration, ad injector, and so on, if this is possible. The role is not to fully label every detection, but just those representative samples that are mostly interesting for the classifier. For example, those that lie on the decision boundaries of each classifier. So let's have a look on how does the loop or classification architecture looks like now. We have the classification module, where are the general classifiers. They produce the detections. They go to the active learning module. And from the active learning module, we can just easily close the loop and return the feedback from the human analyst to the classification module. Right now, we have also the categorical labels. Therefore, we can train not only binary classifiers anymore, but we train directly multi-class classifier that output information on what kind of malicious behavior it was. And again, along with the general classifiers, they produce detections that go to the active learning, and this is how we close the loop. In order to train the models, we use mainly Spark, but not only Spark, but mainly Spark. And to retrain the models takes around 1 to 2 days on a 200 CPUs cluster and on tens of millions of samples. Okay, and just in summary, okay, so we defined the automatic retraining loop, and now from the time perspective, how does it look like? Now, at each point on the time axis represents a situation where we got new samples, new labels from the active learning module. Whenever we got them, we can retrain the model or train a new model and store the model. But at the same time, back in time, we already did that, and we already had some models trained. So these models are already running on the same data, and we can just update their statistics in form of precision and accuracy, how well they perform, given the new labels from the activity learning module. And in this way, we can just easily pick any best working model at a given time and use the model in the production environment. And at the same time, we just store all the updated results of each individual models. And whenever something goes wrong, we just can easily return to any model that behaves still the best. Now this is the end of the theory, and I give back word to Veronika, and she will show you some real examples.
Yeah, thank you. So back to reality. The interesting thing, so we saw how to go from this, right, to this. And for a threat analyst, this is huge already, because it saves a lot of time, believe me. So right now I'm going to show you some examples of these groups and what did we actually find with all these tools and algorithms. So the first example is going to be about the DNS changer. And no, it's not the old DNS changer, it's a new one. So back in the beginning of the year, we deployed a new multi-instance learning classifier that was training in hundreds of different malware behaviors. And as usual, we were so eager to know how it performed. So When I do analysis, I usually group coherent behaviors because analyzing flow by flow is too time-consuming. So I took all the incidents generated by this MIL classifier, that's the orange, and I start grouping things together and say, okay, which group is more interesting to look at? And that was the yellow one. So when I look into it, into the flows, which is the source of truth, the URL looks like this. And it's not straightforward that it's malicious. It's quite interesting though. So we start looking into a bit more deeply into this. There are many interesting features in here. Basically, the domains were changing. The URL was not encoded in any known encoding scheme. So it was quite interesting. Another factor was that suddenly in the first week we saw a spike of from 0 to 500 users infected, which for malware is not so common. So we were kind of reluctant to believe this. We managed to get one sample because one binary, because we look at the network and sometimes it's very hard to actually get the malicious binary that generates the traffic. In this case, we found it, and thanks to our colleague Roskid, he did the reverse engineering and he found that this small Trojan was a DNS changer Trojan. And the communication that we were seeing, it was actually the command and control communication. And in those long URL, it was sending a lot of information about the user. But it didn't end there, because, well, the DNS changer Trojan, for those who don't know, is basically doing something very small and very simple, that is changing the name servers of your computer. It basically means when you try to go to Google, you ask for an IP, your name server will return you an IP. In this case, because the name servers were compromised, if you want to visit Google, you will get a malicious IP, and then they can do anything, return you a web page with infected code, and so on and so on. So we started looking at this, how the users got infected with this. Thanks to the reverse engineering, we found that this was actually delivered by another Trojan that was called Mamba. Mamba is a Python malware that has basically can update itself. So the first stage was once it was deployed, then it will download from a file server another version of itself, and then it will download the DNS changer Trojan. And we went one step further, and we start correlating this with, okay, how did the users actually got infected with this Mamba Trojan? And we found that most of the infections we couldn't prove completely. We are still working on that, but there was a strong correlation, meaning out of 10 infections, 9 were having other infections like Optimizer Pro installed on the system. And actually in the communication of the DNS changer Trojan, we saw the malware reporting these names of adware to the command and control. So this was one of the first findings, and this is how, in summary, very constrained, the command and control looks like. So you can see how the malware is changing the domains, right? Also changing the IPs, and also changing the URLs. But there are some things that, as we saw in the beginning of the talks, are kind of invariant. In this case, it's a path and some parameter names, which some of them are also changing because we have A and Q at the beginning. So this is why these algorithms are good at. So they can actually be smart and say, okay, this looks different, but actually they look the same, right? So they can do that for us. It was quite interesting. Another case that we are still investigating, we found a couple of months ago, it's very curious. It's about advertising gone rogue. We found this traffic in the network. This looks at first sight very malicious. It's DGA domains, random path or resources, random parameter names, which actually point to the same type of content, like the referrer doesn't say referrer, but it says some random parameter names. So we start digging into this. we actually found a different behavior related to this traffic, and it's actually that after some time they were downloading some Flash file, which thanks to also our colleague Rosgiv, and we also have a second opinion from our colleagues in Avast, it's not malicious by itself, it's not an exploit, but it may be part of the re-exploit infection chain, because this Flash file is really small. It contains fingerprinting logic, basically getting information from your computer, what system you have installed, etc. So, and in at least one couple of cases that we can reproduce, we actually got exploited by this re-exploit and dropping the Hansitor dropper. So I went further because I wanted to know, another note to note in this slide is all the strings in this Flash file and also other communication of this traffic. We found that references to popads.net. That's where the part of the advertising comes in. So I was investigating and say, okay, but this is advertising, this is supposed to be legitimate or not. So I actually did a mapping of the infrastructure to try to understand if this is a systematic way of doing this or not. So I mapped all the host names and how long they were active. And actually, I hope you see the animation. This is the host names and how long they are active. And you can see that it's reducing and they are changing a lot. Almost in the end, they are active for only one day and they just go offline. And this is supposed to be legitimate advertising, which I don't think so. So another thing that I wanted to talk about to finish is once as a threat hunter, once you find something, which is super cool, you are done. You want to move on, right? You don't want to be maintaining the IOC's list of the same malware over and over. You are stuck with that. So it's not fun. So how we can mix all these things together? We already saw that we can actually train very specific classifiers, right? So what if the algorithms can take care of this tracking and not me? That can be great. So this is what we did and put in place. And basically, the yellow is the initial set of IOCs, which was around a dozen host names, and this is kind of the size of the infections. And the yellow is the initial thing that we use for training, to say, okay, the algorithm, please learn this, okay? Please learn this, that I want to track it. Then we deploy the classifier. You can see the blue. After some time, the classifier is able to actually start generating incidents on base of this behavior, based on this behavior, completely alone, and it's much more than we actually could capture with the initial IOCs, right? So actually 3 times more detections, and didn't require me any type of interaction, which is great. So we are doing this with more than 100 campaigns, and it's very useful because actually you can have the experts focusing on what matters the most, which is actually finding new things, and leave the maintenance for the machines. So to conclude, we presented how we can create models that are invariant to these network traffic changes, which is very important to capture all this dynamic behavior of malware. We also presented how we can use these weak labels, whether it's feeds, blacklist, anything that is, sometimes they are very good, sometimes they are not so reliable, and we can use these to learn at large scale. And we can also show how we use active learning to actually automatically track malware. And we use this, as we say in the beginning, we are using this combination of things in real life, and more in networks covering in total more than 1 million users, and finding tens of thousands of infections. And this is good news and bad news. The bad news is that these tens of thousands of infections are infections that bypass everything we have in place right now. Because you have to have in place everything, but you can also do these finding infections after, like threat hunting. So this leaves us with this, that what got us here won't get us there, right? We have IDSs, we have antiviruses, we have everything. And it's great, we should keep those. But we should also think about the future and how we start mixing all these techniques together, because we can do much more, and we should. And this is why we are here today talking about this. So, thank you. I think we have time for questions, if anyone has questions. No questions? Oh, over there? Oh, okay.
So the classifier is based on sort of one label. So if you give it sort of good traffic, you know what good traffic looks like. And sort of do something normally question on that.
Yes, I mean, the number of samples, right, for training, how many samples we can in fact use and to train a reliable system. That depends, right? Depends how the sample looks like, or how diverse it is, or how different it is from the rest of the traffic. So of course we can, even for just singles of samples, train a reliable classifier, but it's not almost the case. It's just strongly depends. But still, we just what we do, everything we have, maybe just one sample, we train the model still, and what we do, we just re-evaluate it over the time, whenever new labels are available, and when we see that it behaves correctly, then it is deployed, right? But this is done automatically. You don't have to care. You just use it, train it, see that it works, and deploy.
Any other questions? Okay.
Are there any other cases that you've tested this out on beyond using GGA analytics?
Yeah, sure. We have a kind of a lot of classifiers. It was just for illustration because there are the most cases, or the one that people know. But we have around 70 different classifiers, small classifiers, classifying generic behavior. And then these are then combined into these categories. And we have around 20 or 30 different malware categories that we can classify right now. As ad injector, ransomware, exfiltration, and so on. And they're still increasing. Yeah, so definitely more.
Yeah. Right now we are using mainly proxy logs, which that restricts many things, but we already started to work to move these techniques to NetFlow, which will give us more insight on other protocols, but we don't have any results yet on that. Any other question that I'm not seeing? Yeah?
When you say what data scale one get that there,
Yeah.
what do you imply? That you need the threat hunting? That's the message?
I think that we should be more bold and start combining things in a different way, shaking things up, because we have in place many traditional things, and many people, right now there are hundreds of companies saying we do machine learning, but it's not only about machine learning. We only can catch, we work on the network, so we are already, you are already infected if we see the traffic, right? So I mean, in the sense that anything, so far we have this unique product that will protect you from everything, and this is not going to work. It doesn't work right now, it's not going to work in 5 years. So we need to change things up, so start thinking security differently. Yeah. Okay, no more questions? Okay, thank you very much.
Thank you.